Siri started 25 minutes ago. Alright guys, let me have your attention please. We're going to go ahead and get started. Little minor emo moment. This is the last time I'm going to teach you guys anything. Makes me a little sad. Was it?
Yes.
Well, I have to teach the lesson, so.
Well, I understand that, but that's maybe sad.
You're right, I didn't have to.
Yeah,
that was a strategic choice. I'm really trying to manipulate you into listening. Come on, it's my last lesson.
As we're treating you the same we always do.
I appreciate it.
You're right. All right. So normally, I would have started this lesson off by having you guys do an egg smash. I didn't do that because I wasn't going to. What I normally do is I give you two eggs, one that's boiled and one that is not. And there's a couple of students that can tell visually which one's which, but most students can't. And so then it's up to you to figure out which one is which one's boiled and which one's just raw. And then I make you pick one to smash, right? Which is why I always hope that somebody smashes the wrong one, because I like seeing somebody have to clean up, smushed egg from the table. It's just fun for me. So you can use physics concepts to tell which is which, right? And what students normally figure out is that if you spin both eggs, they spin differently. If you spin the boiled egg, it'll spin really easily and it'll keep going. If you spin the raw egg, it doesn't want to spin. It's like when you try to spin it, it just doesn't do it. Now, the reason for this is what I'm trying to get to you guys with that activity is that they both have reasonably the same mass. They both have reasonably the same dimensions, right? What's different about them is how that mass is distributed inside the egg. So with the boiled egg, it's all stationary, it can't move. But what happens with the raw egg is when you try to spin it, the mass kind of redistributes to the outside, and it makes it harder to spin. So the important bit here is that there's something about the way that I distribute mass that makes things easier or harder to rotate, right? And that leads us into this idea of moment of inertia. So moment of inertia is the rotational analog for mass. It's going to tell us how resistant an object is to spinning. We're gonna do this again today. Y'all just going to be goofy McGiggles in the back, and then I'm going to have to try and focus. Come on now. Tells a lot about you two, personally, that Cameron is making eye contact and you're just looking away.
When I look at her, she's laughing.
It's fine. You have nothing to prove to me. You're not going to have to see me anymore in a couple days.
Okay.
All right. So, moments of inertia, right? That's what we're here to talk about. So I'm going to skip over the agenda and the objectives. Why aren't you clicking? Thank you. Thank you. All right. So look, moment inertia, I just told you guys it is an object's resistance to motion. We use an I for it. I think technically that might be an iota, but it's the same thing. The way that you do this, if you have a few distinct objects, is you use this summation, where for every object I, you multiply its mass times its distance from the point of rotation. That's what the R is, the distance from the point of rotation. You square that, multiply by mass, and then you add it up with all the other ones, right? So we've seen these summation statements before, right? We saw them with center of gravity yesterday. So that's what we do if we have multiple things. So for example, you'll see questions like this that'll be like, this is a good example actually. So if I take something like this, if I pretend that the rod is massless, but that the two balls at the end have mass, right? I could use this equation to find the moment of inertia of this system of objects. Okay? I would say, well, the rod is massless, so it's not an object, right? So I'm kind of cheating. But then the two balls are, say, like 1 kilogram each, and they're both, I don't know, half a meter from the point of rotation. And so then I could use that, and it would be mr squared plus mr squared. Now I have the moment of inertia. Does that make any sense? Mm-hmm. Now, that works really well for systems of objects like that. But what happens is, I have, oh, here's another example with, 4 things. We're not going to do it. I have complex objects, like geometric objects, like cylinders and spheres and hoops and all these kinds of things. Well, if I go back to that other equation real quick, if I take this and I do calculus with it, and I basically treat a sphere as a collection of particles, right? And then I use calculus to figure out if I have, essentially infinitely many of these particles that are in this arrangement, then I could use terms to figure out what the moment of inertia is for that object. And you're not going to have to do the calculus here, but that's how they get it. They take this statement and they do like integration over different objects. You'll probably do that if you take calculus. And what we get are these equations. So what I want you to notice about these equations is this is the moment of inertia of a cylinder. This is the moment of inertia of a sphere. Look, they're both mr squared, the mass of the object, the radius of the object, multiplied by a coefficient. And so when you use that equation with these objects, you will always get some coefficient times mr squared. These are not things you have to memorize. They're not on your formula sheet, but they will give them to you in the questions if you need them. Okay? So be aware that the moment of inertia doesn't just depend on the mass of the object, it also depends on the shape of the object and the radius of the object. So it's a complicated thing. We have special equations for it. Does that make any sense?
Yeah.
Okay. So, the important bit for today is you'll get equations to calculate the moment of inertia, and the moment of inertia is the object's resistance to motion. Which brings us to trying to rewrite Newton's second law in rotational analog terms. So we have Newton's second law was this, that the net force on an object is equal to its mass times its acceleration, right? Well, if you didn't pick up on this trend yesterday, what happens with all of rotation is basically I can just rebuild the system using rotational analogs. So instead of forces, I'm looking at a rotation, so what I really care about is torques. So instead of net force, let's say net torque, which remember is tau. Remember, the mass is enough information to know how something resists rotation. What I need is moment of inertia. So I'm going to put moment of inertia, I, or iota. And I'm not worried about linear acceleration, I'm worried about angular acceleration. And if I plug that in, then I have alpha. So this very well could be a viable rotational analog for Newton's second law. And I would just have to kind of test that. And what's interesting is, if you look at this system and you just rewrite this as FR, and you rewrite this as mr squared, and you rewrite this as r times acceleration, you actually end up getting it to simplify down to this statement, which would tell us that this is a perfectly acceptable analog equation. And so that's what we get. Actually, let's go ahead and talk about this here. So remember, the point of Newton's second law is it tells me if I put these forces on an object, here's how that object will accelerate, and that object's going to resist acceleration according to its mass. Well, what I see here is this is telling me the same story for rotation. If I put these torques on an object, it's going to experience this angular acceleration, which is proportional to how much it resists rotating, which is the moment of inertia. So you will see questions that mirror those Newton's second law questions, like the mathematical analysis questions we did with forces. You'll see questions that mirror those using this. Does that make any sense? All the same techniques that I taught you then still work. So I would still advocate for system schema, free body diagram, mathematical statements. You'll need to make mathematical torque statements there. That's one addition you'll have to do. And then go ahead and do Newton's second law statements and your torque statement, because you never know which one's going to be useful. So you just do all those, and then you can beat it to death with algebra. So it's kind of the same system. Does that make any sense? Yes, no, maybe?
Yeah.
Okay. All right, so that's that. That's really all you need to know there. I think I had an example here, but we're not going to do it. What questions do you guys have about the concept of moment inertia or Newton's second law for rotation? Yeah.
So, to kind of reiterate what you just said, so when solving for rotational objects, it's the same thing as free body diagrams. You draw, and then you, instead of doing the regular Newton second law statement, you do the torque one.
Yes. So two ways I'm going to take your question. One is, yes, that's accurate. I would tell you, in addition to a free body diagram, I would also try and draw a diagram where I'm looking at the actual forces on the body. So, for example, if I'm let's do this. If I am pulling a nail out of the ground, so let's say I got a nail here and I've got a hammer that's hooked around it, like that. Well, I could do a free body diagram of the hammer, right? And what I would notice is if I pull this way, then the free body diagram is going to look something like this, where I've got the force I'm applying, the force that the nail is applying, the force of gravity on the hammer, the normal force on the hammer, and so I think that's it. Something like that, right? So the free body diagram there is helpful, but what would be actually better is for me to have some sort of diagram to help me understand what's happening with the torques, and to do that I need to know where all of those things are. So in addition to that, I would recommend drawing kind of a simplified diagram where I could say, okay, here is the force of the nail, and then the normal force is acting here, and the force of gravity is acting at the center of mass here, and there's probably some sort of frictional force which I didn't include. Oh, that was the applied force. The applied force is here. Because the torque is determined not just by the force itself, but also where you apply it. And so drawing some sort of diagram where I can visually see the point of rotation is down here. And so this force is going to apply a torque because it's away from that point. This force is going to apply a torque. And that will help me understand, like, which forces am I really comparing with torque. Because if you dig into this situation, you'll see this has no torque and this has no torque. So I'm really only comparing those two when I'm looking at the torque. Does that make any sense? So a simplified picture where you can kind of determine who's having torque and who's not would be a nice additional step. The other thing that I will tell you is most often you'll either be looking at rotation or you'll be looking at translation. But there are certain questions where you'll have to do all three. So for example, physics loves what they call ladder questions. So something like, hey, I've got a ladder leaned against a wall. And if they really hate you, it'll be like, and there's a person standing on it. And they'll ask you, like, you know, what's the coefficient of friction got to be over here to keep the ladder from slipping, or something like that, right? Well, with this type of question, it's an equilibrium question. Remember yesterday we talked about the different equilibrium conditions. You would have to do 3 different mathematical statements saying the sum of the force in the x is 0, the sum of the force in the y is 0, and the sum of the torques is 0. And so now you have to use these 3 and then go do the same thing that I did before. And again, I would recommend taking this and doing a simplified diagram and saying, here's my ladder. So I've got, friction and I've got a normal force, and then I've got the force of gravity of this person, the force of gravity of the ladder, and then there's some sort of normal force against the wall, so that now I can see like where all those things are. And again, if this is my point of rotation, then I would know no torque, these are the ones that have torque to worry about. And so drawing a little diagram so you can think through that stuff is really helpful. This is the kind of stuff that like, I'm focusing on making sure you understand kind of the core concepts instead of being able to jump into like how do you use this to problem solve. But Lord willing, I'll be coming back like a couple Saturdays a month to help coach you guys on that kind of stuff. So as you're going through it, then we'll do that. So anyways, that's a couple different ways to take that question. Any other questions on this? So as is kind of standard with physics, bruh.
Sorry. I tried to turn it down.
As is standard with physics, oh my god.
Just turn it off. It's not turning off.
Why don't you just take a second and fix it?
Yeah.
Is it fixed? It's fine.
No,
It's good? Okay, cool. All right. So, as is standard with physics, hopefully you guys have caught on to this idea that like, I think that the core concepts of physics are not very complicated, right? It's where you start having to like apply mathematics to that and use it to build models is where physics gets hard. And so over the last couple of weeks, I've been focusing on like, here are the core concepts. And so my hope is that as you go through stuff, you'll have a decent grip on those core concepts. And then hopefully there will be somebody here who can help you with the mathematical modeling. And if not, then I'll come back around if the school will let me, and I'll try to help you guys out with that. Which, by the way, side note, I'm going to stop the camera real quick because I'm done with that lesson. Unless anybody has any other questions.
No.
Okay.